This time, we are going to determine whether this set of x vectors, which of these four is considered as an eigenvector of the 3 by 3 matrix given here as matrix A with the following entries. So here we are going to try using each of these vectors and verify whether which of them again is an eigenvector. But before we go to that, there's an important theorem which tells us that for an n by n square matrix, the number of eigenvalue together with eigenvector is at most n. And since this is a 3 by 3 matrix, we know that there is at most 3 of them. So out from this 4, there is at most 3. So there could be none, there could be 1, 2, or 3, but it can never reach 4. Of course, once we are able to determine the 3 of them, and if in case we still have one more to try, we're going to show it as well. So how do we determine whether these vectors, x vectors, are eigenvector? It should satisfy this equation, where the product of your matrix A and the chosen vector, x vector, must be equal to a certain lambda times the same vector. In short, we are going to multiply this first, and after that, whatever be the result, let us try to examine if we could present it in this form where we factor a certain lambda, let's say a scalar, any scalar value lambda, and that the same vector used here will reappear. And if that's the case, the said vector used is an eigenvector of matrix A. So let's start with the matrix, the vector x, or x vector in letter A. So let's try to start it like this. And of course, our A is -1, -1, 1, -2, 0, -2, 3, -3, and then 1 here. We're going to multiply the first vector that's on letter A to -4 and 6. Notice here that this is a 3 by 3 matrix, while our vector is a 3 by 1 matrix. In short, we are expected to have a result which is also in a 3 by 1 matrix. And we simply multiply them. -2 times 2 is -1 times 2 is -2. You have -1 times -4 is +4. Okay? 1 times 6 is 6. So you have -2, +4, and +6. You will have +8. You could try to use your calculators there if you would like to. -2 times 2 is -2. -1 times is -2 rather. Then you have +4, +6. That's why you have +8. Next, you will have -2 times 2 is -4. This is 0. You have -2 times 6 is -12. So you have -4 and -12. That's -16. And finally, for the last, 3 times 2 is 6. -3 times -4 is 12. Then 1 times 6 is also 6. You have 6, 12, and 6. Again, let's do it again. You have here 3 times 2 is 6. This is +12. That's another 6. So you have 24 here. This is the result of your A times your vector x. Now, let's try to examine if you could factor a certain lambda here, which will in return have a matrix here that is similar to this. Of course, 8, -16, and 24, you could always use here 8, right? Okay? Once you factor out 8, this will become 1. Okay? This will become -2, this will become 3. However, let's not use 8 because the goal here is to make sure that this matrix here will return to your same vector. So instead of 8, just for the purpose of illustrating whether this is an eigenvector or not, let's try to take a relationship of 8 and 2. So instead of 8, we'll have 4, so that what retains here is 2, because that's 4 times 2 is 8. The same value will be removed or factored from -16, so you have -4 here. And when you factor out as well 4 into 24, you will have our result. Sorry, let's do it again without the circles on our result. Okay, yeah, that's the one. Okay, so that you could really see the difference now. So again, we will be using 4, and this will become 2. This will become -4, and when you factor 4 to 24, that's 6 here. This is now the same as the vector used. In short, when your lambda is 4, it satisfies the situation of the product of lambda and x. This means that the vector in letter A is yes, it's an eigenvector of matrix A with the corresponding lambda equal to 4. This is what you call as the eigenvalue of the corresponding eigenvector. Okay, so we have specified already the first one. So let's proceed to letter B. So A times vector x as well. That's x. So you have A, -1, -1, and 1, -2, 0, -2, 3, -3, and 1 to be multiplied with the next vector, 2, 0, and 6. Okay? 2, 0, and 6 here. Same thing, 3 by 3, and then 3 by 1. So we are expecting to have a result which is also a 3 by 1 matrix. And let's try to solve them step by step. -1 times 2 is -2. This is 0. That's 6, right? -2 and 6, you have 4. Then, -2 times 2 is -4. Another 0. Then, -2 times 6 is -12. -4, -12. So you have -16. Then, you have 3 times 2 is 6. This is another 0. 1 times 6 is 6. 6 and 6 is 12. These are the result of A times your chosen vector x. So let's try to examine if there's a certain lambda here which can be factored out and will return to this. However, look at the second entry of your original vector. That's 0. When can this be 0? Okay? That would mean your lambda here is 0, so that your result here is still 0. Okay? Or you could even that is another hint that you can use, because if your second entry here is 0, that would mean your lambda here can take any value, and that's very flexible. However, let's look at the first entry, 4 and 2. So what happens to 4 and 2? You will take out 2, right? So you have 4 and 2, you will have 2 here. Okay? However, when you take out 2 from 16, okay, this is what I mentioned earlier. It should be 0, right? When can this 16 be 0? It can only be 0 if your lambda here is 0. But since it's not 0, it's 2, when you factor out 2 here, that's -8. Even if your third, when you factor out 2, it's 6. Even if your first and third entry matches your original vector, your second entry is not 0. This would mean this was not achieved, and your x vector in letter B is not a eigenvector, an eigenvector of matrix A. So we are down with that. Earlier, we mentioned that there are at most 3 eigenvectors here because of a certain theorem. So we have verified A to be an eigenvector and B which is not. Does this automatically mean that your next 2 vectors here are also eigenvectors? You may say yes, you may say no, but for the purpose of this illustration, let's move further. Let's try to move to letter C with the same process. So your vector here, your vector here is -1. It's here. You can see in letter A. -1, -1, and 1. -2, 0, -2. That's a 3, -3, and 1 to be multiplied with your third vector, 2, 2, and 0. 2, 2, and 0. So we also have another 0 entry here. So you need to really understand how that is very important when you're dealing with operations later. So let's have here, -1 and 2 is -2. negative 2, that's 0, so you have negative 4 here. Next, negative 2 times 6, negative 4, that's 0, so negative 4 here as well. And for the last one, 3 times 2 is 6, negative 3 times 2 is also negative 6, that's 0. 6 minus 6, you have here 0. Let's try to examine. Of course, our third entry is 0 and 0, unlike earlier where it's 0 and 16. So more or less, there can be a way to show it correctly. But of course, your goal here is this vector. So to make this negative 2, you can take a certain lambda, which is equal to negative 2. And what happens to your entries here will become positive 2, right? Negative 2 times 2 is negative 4, that's correct. Since it is also negative 4, that's positive 2. And since it is 0, no matter would be the value of the lambda here, it's still 0. Because once you multiply negative 2 times 0, it just returns to this value. Look at the two vectors. They are the same. In short, the x vector in letter C is also an eigenvector of matrix A, where lambda is negative 2, or more specifically, where the eigenvalue of the given eigenvector is negative 2. So we have 2 now. So again, letter D, still to verify. So you have negative 1, and 1, negative 2, 0, negative 2, 3, negative 3, and 1, to be multiplied with your x vector in letter D, negative 1, 0, and 1. Negative 1, 0, and 1. So 3 by 3 times 3 by 1 is also a 3 by 1 matrix. Negative 1 times negative 1 is positive 1. This is 0. 1 times 1 is 1. So 1 plus 1 earlier, you will have 2. Okay, because negative 1 times negative 1 is 1. You also have another 1. This is 0. That's 2. Next, you have negative 2 times negative 1 is positive 2. This is 0. This is negative 2. Positive 2, negative 2. Your second entry is 0. Next, 3 times negative 1 is negative 3. You will have negative 3 times 0 is 0. 1 times 1 is 1. So you have negative 3, and in positive 1, you have negative 2 here. So this should be lambda something matrix that will return here. So what lambda do you think? Of course, your original vector has negative 1. This is positive 2. So what you can take here is negative 2. Okay? So that when you take out negative 2, this is negative 1 here. Right? And then you have 0 and 0. Okay? Because when you this is just 0. No matter what constant you take out, it's still 0. And negative 2, when you take out this, you have positive 1. See that it meets the original vector. In short, the vector in letter D is also an eigenvector with the same lambda of negative 2 as this one here. And this is also the eigenvalue for the specific eigenvector. Okay? This is how we verify the presence of an eigenvector in terms of vector x that will satisfy the given matrix together with the correct eigenvalues. Thank you very much for watching.